second.
Hey, Gary.
Bienvenue au séminaire en informatique. Notre conférencier, Jacob Feldman, un instant, je vais regarder. Il est professeur de psychologie de sciences et de sciences cognitives à l'université de Rutgers, où il dirige le Visual Cognition Lab. Ses travaux portent sur les modèles computationnels de la perception visuelle humaine et de l'apprentissage des concepts, notamment l'organisation perceptive, la représentation des formes et la catégorisation. In other words, Jacob, you're very similar to the area that I work in. OK. Il a également contribué à l'étude du principe de simplicité dans l'apprentissage des concepts, à la minimisation de la complexité booléenne, ainsi qu'au développement de modèles bayésiens et de la perception et de la perception et de l'apprentissage. Son titre, le titre de sa conférence est Les humains et les machines face au jeu des règles cachées. Je ne vais pas vous lire le résumé parce que vous l'avez déjà. And now I'm going to switch to English. Everybody in the distance has seen your bio and has seen your abstract, so I needn't repeat that as well. I'm very happy to have you here in Montreal. I assume you've been here before, Jacob.
Yes, not to the university, I don't think, but to the city.
Okay, very good. I'm happy that you're here and giving this talk, and I'm going to hand the reins to you. What Jacob has agreed to is that if you, I'll say it in French first. Si vous avez des questions, posez-les à l'instant, il va répondre. And so if you have any questions, he'll answer during his talk. And for that reason, he's released from all time limits on his talk. Well, not all time limits, until noon.
Right.
Okay, Jacob.
Okay, thank you, Stephen. So I want to say first that I am going to speak in English. I hope that's okay with everybody. Thank you, Stephen, for the opportunity to give this presentation of this project that my collaborators and I have been working on about the game of hidden rules. Let me say before I start that this is a collaborative project with my friends Paul Cantor, Hao Wang, Lazarus Gallus, and Vladimir Menkov. Paul is really the guru of the group and the original creator of the game of hidden rules, although I have to say I don't think he will agree with everything I'm about to say about it. And I also want to acknowledge funding from DARPA. Okay, so sorry, my remote working? So as a broad preview of the talk, this project is about studying similarities and differences between AI and human intelligence, which I'll sometimes call HI. And the general idea is to compare them on a common task. So, I mean, as a bit of a table setting, there's an enormous amount of discussion, especially in the last 10 years, of the similarities between modern AI, neural network-based AI, and human intelligence. But as a psychologist, I will say a lot of it is based on kind of speculation or assumptions about human cognition, also about AI sometimes. And the goal here is to actually study them both empirically. We're going to actually perform experiments on a common task in both AI and human intelligence, and actually see how they perform. So the common task is called the game of hidden rules, and I'll show it to you in a minute. It's a simple rule discovery game in which people have to sort, or AI has to sort colored objects into categories or into buckets, and there's a hidden rule that tells them which piece goes in which bucket or which moves are allowed, but they don't know the rule at first, and they have to discover it by trial and error. I'll show you this in a minute. People can play this, and the point is that AI can also play it, so it's a level playing field. And overall, the goal is to understand human intelligence. I mean, I'm a psychologist and a cognitive scientist, so my overall goal is really to understand human intelligence. But because we still think that human intelligence is kind of the gold standard for intelligence, I know that's somewhat more debatable in a lot of public discussion of this these days, but human intelligence still works very well, and AI may or may not work very well. So a secondary goal is to potentially improve AI by understanding ways in which it's deficient relative to human performance. So I want to start by kind of framing this around a little bit of my skepticism, because as I said, I'm like a lot of cognitive scientists, I'm kind of skeptical of modern neural network models as being very similar to human intelligence. Um, I don't like kind of glib comments that that it works just the same way that humans do because it's also a neural network. We don't really know how human intelligence works yet. We're still working on it. So we don't know that they're necessarily very similar. But at the same time, I'm leery of kind of pat statements about how different they are because human intelligence is not magic. Sometimes one hears this idea that people have some kind of deep sentience or understanding that AI can never achieve. And that I think is kind of begging the question a little bit because human intelligence is also some sort of computational mechanism, if only we understand what it is. So with that in mind, before I tell you about the game of hidden rules, I want to kind of make a comment about the Turing test and what it means for AI to resemble human performance. And this will also kind of set the stage for how we approach the game of hidden rules. So if you bear with me for a couple of minutes before I get to the actual game. Let me just say something about the Turing test. So a very common objection to the Turing test years ago, I don't think that Turing himself raised it, but is the idea that there can be what are called canned responses, meaning that a human programmer could pre-compose answers to every possible question that the computer could be asked and every possible follow-up question, et cetera. And I hope that people have the intuition that if that were to happen, that thought experiment, then the computer would pass the test because its answers would be, by definition, indistinguishable from those of a human, because they would actually have been written by a human. But at the same time, I hope you'll agree that that doesn't really, in the spirit of the test, it's not really passing the test because it didn't actually generate its own responses. It just was, copying them from a lookup table from some human responses. So historically, that objection was a little bit of an asterisk because it was assumed to be impossible to actually do that because it would take an implausibly large memory to carry it out, because there's an astronomical number of possible questions and possible follow-up questions, etc. The phrase one used to hear is you would need a disk drive the size of the solar system. Or honestly, it was bigger than that. Somebody calculated once it would be a disk drive the size of the universe. Um, but I think that skepticism, which comes from an earlier generation, turns out to be a little bit misplaced because people under Turing may have underestimated, but earlier generations underestimated how big our disk drives would get, so to speak. So GPT-3 has, something like 10 to the 11th parameters. That was the first version of GPT that became very known to the public. GPT-4 version that was somewhat more mature has about 10 to the 12th parameters. The current version has something a larger number of 10 to the 12th. This is something like 1 trillion parameters. So that's not the size of the solar system, but it is very, very large. Large to a degree that I think people don't have even clear intuitions about what a large database it's been trained from. The question is not, can we construct a disk drive to hold all the canned responses, but rather, can we compress that disk drive into a lossy compression that is sufficiently predictive that it can fit into a server farm? And so, like, this is ironically, a computer-generated image of a server farm that OpenAI is building in Texas. To give you a sense of the size, that's just disk drives. So, as a little bit of quantitative comment, the internet has about 10 to the 15th bytes. Again, that's a rough estimate. Nobody really knows. And GPT-5, has about 10 to the 12th. So the ratio is something like 1,000 to 1, which is not an incredibly microscopic ratio, meaning that essentially GPT-5, when you're talking to it, you're kind of talking to a compressed version of the entire knowledge of the human race. So, just to beat the horse into the ground, the Turing test really only counts if the computer is causally responsible for its responses. So let me give you some examples. So this is a little passage from Turing's original article where the hypothetical judge asks the hypothetical computer to answer a few questions about Christmas. Um, if it turned out that those pretty plausible sounding answers were actually generated by a human who had canned the responses, I think we would agree that it's not really passing the Turing test in spirit in any case. Um, Similarly, if you have a robot that is, for example, emptying your dishwasher, this is a real example from just a few months ago. A lot of publicity about this Norwegian robotics company had a robot that could really, you know, unload your dishwasher, do other household chores. But then it turns out it's actually being operated by a remote human teleoperator with a headset, which turned out to be true. I think you would agree it's not really intelligent. It's simply impressively engineered mimicking of human behavior. And so that leads to the question of when you talk to ChatGPT or some contemporary LLM, if it's actually a lossy compression of human behavior, the question is, does that really count as passing the Turing test? So I know there's a lot of discussion about whether these current AI models pass the Turing test. And I just want to frame this by saying that that's not really an interesting question to me because they are heavily, heavily, heavily trained on human behavior. So in a sense, you're just talking to other humans. Um, so that's not the main topic of this talk, but it's a frame for saying how we approach the game of hidden rules. So for the most part, I'm going to avoid AI models that are trained on human behavior, because the question is not whether the AI can imitate humans. It can. I mean, that's what current AI models do. But the question is whether it can think, and I deliberately put that in quotes because, as Turing pointed out, that's kind of a vague word. The question is whether it can do human-like cognition in a way that doesn't depend on a human having done it first. And as I said before, I don't want to evaluate AI models against our assumptions about how humans work. Instead, I want to actually test them. So all that leads to the game of hidden rules, which, by the way, I will show it to you in a minute, but this is something that is public and you can play the game and learn about the background of the game and see site references to papers, previous papers about the game at this link. Um, okay, here's how the game actually works. You have a bunch of random objects, as I said. Here's a typical screen. There's a bunch of, red circle, black star, etc. They're in random positions, and they have different features and etc. Different shapes and colors. The user's job is to sort them into the 4 buckets that are at the corners. And again, on the very first move, you have literally no idea what to do. You might just randomly try something. But eventually, after they're either accepted into a bucket or not accepted into a bucket, you begin to get the idea. And there's some sort of hidden rule that's actually governing which ones could go in which buckets. And eventually, a human user usually will figure out that rule or some approximation to that rule and be able to do a lot of pieces correctly in a row. Some of the rules are pretty easy, some of them are harder. So here's a kind of live example. So you can see the user is grabbing the black triangle with the mouse and put it in there. It didn't work. And then tries another same shape into another bucket, here into another bucket, and this time it works, the little happy face. So I'm going to maybe try other black things. Oh, it seems to be working. So we've run out of black things. So let's try another color into another bucket. That one didn't work. So still thinking maybe it's a color rule. And sure enough, the yellow ones seem to go in that bucket. So at this point, the user may be feeling that they've kind of got it. And they finish it up by guessing the other color matches. And at that point, the board is cleared, and then it goes on to a few more boards. And eventually, when the user has solved it, they'll go into a new rule. So here's another different rule, starting from scratch. That red circle went in there. And that red circle also did, so maybe it's red, maybe it's circles. Ooh, this one, I think the user was pretty lucky to start with, and etc. I think I have one more example. Oh, I'm sorry, that one was a second screen of the same first rule. So here's an actual second example. My mistake. So here we're guessing and maybe thinking it's something to do with color or shape, but some of these pieces are not obeying the pattern if you're following the colors here. So you can see that in this case, I mean, the solution is at the bottom, but you can see at this case, no color rule or shape rule seems to work. And eventually the user realizes that only a certain piece is actually movable and they have to be taken off in a certain order, which in this case is reading order, that is rows across left to right, top to bottom. So eventually the user gets it, and you can see that's a pretty different type of rule from the first rule. But people do eventually get these. That one is, I'll show you later, is somewhat harder. Here's some more. Once you've got the rule, you just start peeling them off the board in reading order, and you're good. Let me show you one more example. So here, this one is one that is noticeably trickier. So you can see the first try didn't work, and the second one did work, but then a few other pieces into the bin at the upper right don't seem to fit the pattern of the first piece until eventually the user realizes that actually doesn't matter what color or shape it is. You just have to do certain bins in certain buckets. I'm saying, we used to say the right word, in a certain order, and eventually you see the solution at the bottom. It's alternating buckets 1 and 3. So that's a tricky rule, and people take longer to solve that kind of rule. And there are some generalizations we can make about what rules are easier and harder, which is sort of the point of the project. Although I'll say for today's talk, mostly I'm not going to talk about which rules are easier and harder, but rather how similar human biases in terms of the ease or difficulty of these rules relate to AI biases. So the main point is to compare human behavior on these rules against AI behavior. Okay, so broadly speaking, as you've seen, there are a number of types of rules possible. This is a kind of intuitive classification, but some are feature-based rules like the color match and shape match, which we saw examples of, et cetera. And that's sort of maybe you might think the first thing you'd think of that, these shapes have salient colors and shapes. And so you want to figure out what the rule is about the color or the shape. But some of them are not like that. Some of them are space-based. One I didn't show you an example of is nearest quadrant, which just means basically put each shape into the nearest bucket. And that's pretty intuitive. If you think about a kind of real life analog of that, maybe that's the first thing you would think of, that things just go into the nearby bucket and then you're good. But of course, there are other more complicated space-based rules. And then there are sequence-based rules, like reading order, which we saw an example of, or clockwise, like the buckets have to be, you have to put things in clockwise, and people can figure these out as well. An important point about this is that rules can be composed, meaning that you can combine like a feature-based rule with a space-based rule or two feature-based rules, leading to all kinds of complicated combination rules at various levels of complexity. And I'm going to talk about composite rules a lot later on today, but I'm not really going to talk about complexity per se, but suffice it to say that complex rules are generally harder than easy rules, at least for people. So I'm going to show you a bunch of experiments, and I'm not going to give you details of every different experiment, what the subjects were, et cetera, but let me just broadly characterize the participants. On the human side, we recruited subjects on Prolific to just play these games. Typically, people play 4 rules per session. It takes about half an hour. The only real requirement is that they be proficient in English sufficiently to understand the instructions. And in fact, quite a few primary languages were represented in our subject pool. I should say these details refer to just a big initial experiment that we ran. It's not accurate for every experiment, but roughly representative. So there were like 31 primary languages. About 60% were primarily English speaking. And the age was very, very wide, ranging from 18-year-olds, young adults, up through older people. Mean of 33, and the gender breakdown was pretty close to equal, about half and half. For the AI models, I'll say more details about the model types, but we at various times in the project have tried various AI models. The one that I'm actually going to tell you about is the so-called A2C reinforcement model, transformer model, which is just take my word for it, or really take Hao Wang's word for it, but a state-of-the-art um, uh, modern neural network type of model. I'll say more about it. Okay, so the age, of course, I'm kind of kidding by giving its age, but as I was saying at the beginning, we're not primarily testing models that have been trained on human behavior. These the models I'm going to tell you about are fresh out of the box. They are random initial parameters. They are blank slates, and so in that sense, they're newborn babies. And gender, again, I'm kind of joking by saying the gender of an AI model, but actually, I wish people would notice this generally in discussions of AI. Contemporary AI, like ChatGPT or Gemini, which is trained on human behavior, does in a sense have a gender, because whatever characteristics are gender specific, whether or not there are any such characteristics in human subjects, is going to be imported into the AI. So it's really not a good idea to think about these AIs as kind of autonomous intelligence. They're not. They're just reflections of the training set, which are humans. So, ChatGPT does have some kind of mixed gender. I don't know what the breakdown is. Um, so for the dependent measure, again, just a general characterization of the experiments. For human subjects, there are a number of dependent measures you can use. The main one I'll tell you about is what we just call n moves, which is how many moves before they solved the rule, or honestly, also before they possibly gave up, because they are allowed to give up on a rule if they really can't solve it. Um, so the idea of n moves is that it's a larger number when the rule is more difficult. Of course, if they gave up, then it's underestimating the difficulty, but it's still a large number because they don't usually give up until they've tried many moves. So it's basically a measure of difficulty. And for the AI, a similar measure, which we call M star, there are, again, many measures that one can use here. M star is essentially analogous measure to N moves, meaning it's how many moves before the AI commenced a streak of successful moves. You can adjust the definition a little bit, but it's also a measure of difficulty, meaning more moves required leads to a larger number, a more difficult rule. Okay, with that setup, let me give you some actual empirical results. So initially, as a way of understanding how the game works, we ran a set of 18 rules. We call them fiducial or standard rules, which are just things that are easy to program, a cross-section of things that are easy to program in the language. And here I've ranked them from easier to harder, and I'll give you a few examples. For example, the very easiest one in this list was color match. You can see that code there says CMRBK, et cetera, which is just for which colors were in which bins, but it's a color match. And the second easiest was a shape match. So that, is consistent with the intuition that I was saying before, that a simple feature match between, classes of objects that go in one bucket is kind of relatively easy. And then somewhere in the middle, we get reading order, which is another one that I showed you an example of, and nearest quadrant, which is conceptually a pretty simple rule, but takes people a medium amount of time to discover it. And then the hardest rule in this particular set was arbitrary quadrant, which is basically, each quadrant, quadrant in the space of the board of the screen goes into a particular bucket, but it's not the nearest one; it's some other random one. That's pretty hard for people to discover. The other thing to notice is the y-axis here, which is n moves, and you can see roughly the range of how many moves it takes for people to solve the rule. So hold that in your head when we get to the AI. So to give you a sense of what people are doing over the course of solving one of these rules, let me give you a few typical sequences. So these are plots that show the probability of a correct move as a function of move number as they progress through their attempt to solve the rule. And I've smoothed it so you can see grossly what these look like. And so here's a kind of typical one where somebody started roughly a chance and then gradually began to approach some idea of what the right rule was, and then ends with a streak of good performance, which is that sort of always happens because that's how we decide that the session is over. But so this one gradually got the idea. And this one too. This subject, for example, had no clue. It basically stayed down near chance performance and never really got better. And that does happen quite a bit with humans. Um, but here are a few that are kind of more typical. You can see these huge fluctuations between a high probability of correct with a low probability of correct. And you might think, well, why are they getting worse? But I mean, the answer intuitively is that they're trying different things. They try a rule that maybe works for a while, but that doesn't really seem to carry all the cases. So then they try something else. Maybe it's worse. And so you get one of these valleys where for a while they're getting them all wrong, or mostly wrong. And then eventually they hit upon the correct answer, and then they get up to criterion. And you can see a
Excuse me a
lot.
second,
Yeah,
Jacob. Are you under the impression that you're using your mouse?
no,
Oh, okay.
I'm
Thanks.
just clicking forward, but I haven't been using the
Okay.
cursor, if that's what you mean. I'm sorry, I'm just referring to each image as it appears.
Thanks.
Um, So in a lot of them, you see this kind of fluctuating pattern, followed by eventually some degree of insight. And I'm using the term insight to just mean they solved it, and from then on they get them mostly right. Um, so that's the kind of generalization, an irregular path towards insight. Insight is a kind of a technical term in psychology. It means a qualitative moment of understanding, and exactly what's happening when somebody has insight, of course, is sort of the question. We don't really know, but I'm just using the term loosely to mean that they went from not getting the moves correct to getting moves correct. So that's the pattern with humans. Now let me tell you about the AI. First of all, a few details. As I said before, this is the A2C transformer architecture. Um, I'm not the AI expert, so if anybody has questions, I would have to direct them to one of my collaborators, maybe Paul, who's on the call, could answer. They have an exploration parameter, meaning that they're only trying to improve with some probability with some other probability they try other things that parameter does control and partly how quickly they find the rule. Um, when I show you data about them, we have averaged it over a number of runs with random initial parameters. As I said, these are blank slate models, which in contemporary AI usually means that the parameters are random at the beginning. And what we've done is re-randomize a number of times and retrain it on each rule as I show you. So it's not dependent on any one particular lucky or unlucky streak. There are several versions of this AI that we've tried. There are several different models, but to give you a sense of the scale, they have about 10 to the 8th parameter. So they're highly parameterized models. But as I said, they're not trained on human behavior before the beginning of a game. And as I said before, the dependent measure is m star, number of moves until it gets it to some criteria. Okay, so here is the same set of 18 fiducial rules on the AI. Just to give you an illustration, like color match is somewhere in the middle. Shape match is also somewhere in the middle. Before they were the easiest. Of course, I'll have something more comprehensive to say about how these two plots relate in a moment, but just this gives you a sense that they're not identical. Again, to give you a sense of how the AI progresses through a solution, analogous to how humans progress through a solution, here's a kind of typical plot. All the plots kind of look the same. You can see this, the y-axis here is the error rate, and the x-axis is time, moves or episodes. And obviously, it starts at a high error rate, and it declines more or less monotonically. There is some, some fluctuation, of course, but it kind of inexorably marches towards towards a lower error rate. And you can see like the red dotted line here is the criterion, and you could set the criterion to almost any level. Eventually, it's going to get down to that level. And there's a point at which it hits our criterion, and that the number of episodes or number of moves until it hits that criterion, that's our m star measure. Here's another rule, and it's hard to even tell the difference because they both look the same. Of course, one might be easier, one might be harder, it might take longer or shorter to get to criterion, but they all kind of have this long, slow march towards low errors. So that's the kind of summary. AI always follows an inexorable march towards low errors. And just to visualize this in your mind, remember it's this extremely high dimensional space, and essentially it's moving progressively through that space in little tiny bits, and each point in the space is a policy or a rule that it's trying, and it's not necessarily, it's not represented as an explicit rule. It's just represented as a point in the parameter space, and the error rate at each point in the space is just gradually going to diminish as the model gets feedback from its responses being correct or incorrect. So to give you a gross sense of comparison between AI, you may have noticed the y-axes there were quite different, and that's really the initial very dramatic point about this is that humans are much, 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 much faster at solving these rules. The average human mean across all the rules that we tried in an initial representative set of experiments was about 68 moves, which it takes some patience actually to do that. That's combines some that were much faster and some that were much slower. The AI takes thousands of moves to achieve its criterion, approximately analogous criterion. The ratio is something like 120 to 1. So people can solve these rules, AI can solve these rules, people do it much, much more quickly. But that's not really the question, especially because, of course, they're starting from different starting points. The more interesting question is whether their performance is correlated. If we disregard the absolute numbers, the question is, are they similar to each other? So for the 18 rules that I started with, here's an example plot. So here we have human performance on the x-axis and AI performance on the y-axis, and it looks like a slightly increasing trend But you can see from the Bayes factor in the bottom left corner, there's actually no statistical correlation between these two. And whatever slight trend you might see is really due almost exclusively to 1 or 2 points. That Bayes factor being less than 1 means that there's actually no statistically meaningful correlation. So this slide is really lack of correlation between human and AI performance. So as an initial punchline, humans can solve these rules relatively fast. AI can solve it relatively slowly, but they don't do it in the same way. Now, as I said, there's a lot of caveats for that. So before we critique that result too much, let me move on to what I hope is a somewhat more meaningful comparison, which is about what we call transfer. So you might be objecting in your mind so far um, that human participants are not blank slates. They have a great deal of experience with similar puzzles before they started the game, and the AI by design is a blank slate. So in a sense, that is a kind of asymmetric comparison. The real issue isn't whether they perform similarly, but how they learn from prior experience. So in the human case, they have a ton of prior experience that we can't quantify or learn about easily. But what we can do is give them a rule and then give them another rule and see whether the first rule affects the second rule. And we can do that for AI as well. And then see if the effect that a rule has on another rule for humans is similar to the effect that a rule has on another rule for AI. In psychology, this is called the problem of transfer, and it's a very old problem. What effect does learning something have on something you subsequently learn? That's the kind of core question about whether AI and humans learn the same is, does a particular experience, and in this case, a particular rule, have a similar effect on subsequent learning? So that's the question. How does encountering and or solving one problem affect solutions to future problems? When I say and or solving, what I mean is I'll show you data that's about when we showed people one rule and then showed them another rule. But then in some cases, I'll restrict it to subjects that solved the first rule, not just subjects that saw the first rule. You'll see that doesn't usually make that much of a difference, but it does clean up the data somewhat. Okay, so now let's talk about transfer. So the first transfer experiment that we did involved 6 rules, and we're kind of interested in sort of, you might think of as lateral comparisons between rules. So here are the rules. So I say lateral because it's just from one rule to another rule. So we chose 6 rules that were clumped into 3 kind of semantically meaningful categories. At least they seem semantically meaningful to us. So there are 2 of them were shape matches with different shape mappings. That's with the letters C, S, Q, T, etc. That means like circle, square, star, triangle. That's corresponds to which bucket is which shape. So there were 2 shape matches and 2 bucket order rules, clockwise and counterclockwise, and 2 quad-based rules, which you might think of as spatial rules. That is like nearest bucket, as I mentioned before, is just put each object into the nearest bucket, and specific bucket or arbitrary bucket is you put them into some bucket, but not necessarily the nearest one. You have to learn which one goes into which rule. So in the human experiment, each subject ran 4 rules, but I'm mainly going to talk about rule number 2 as a function of rule number 1. We had them run 4 rules because we didn't want to waste subjects' time, and we have some other interesting manipulations we did in blocks 3 and 4. But for the purpose of this talk, just think of it as 2 rules. And the question is, well, how is their performance on the second rule as a function of which rule they learned or attempted to learn in the first block? So all pairs of those 6 rules appeared equally often among subjects. So there are really 30 separate conditions that 6 choose to total conditions. And the key measure is what we call transfer benefit, conveyed by one rule on the next rule, on the subsequent rule. So let me explain transfer benefit. So the dependent measure is n moves, as I said before. And so again, n moves is lower for easier rules and higher for more difficult rules. And so the main measure of transfer benefit is the reduction in n moves due to the rule. So basically, we look at n when B followed a rule that wasn't A compared to n, the number of moves when B followed A. So that's the transfer from A to B. It's how much smaller, meaning easier, did they find A than B? Did they find B when it was preceded by A compared to B when it was preceded by anything else? So that's a larger number when seeing A improves performance when subsequently seeing B. So I hope that that measure is clear. So let me start with just basic results, psychological results for the humans. So here you can see a plot of the n moves as a function of whether the previous rule was the same, that's on the right, or the previous rule was different, that's on the left. And you can see a big advantage when the previous rule was in the same class, right? Not the same rule, but in the same category, same type of rule. So for example, a color match followed by another color match. So if you can just sort of intuitively put your mind into the mind of the subject, if you see a color match and then later you see another color match, maybe that's the first thing you think of because you think, oh, I guess they're all color matches. And so you just try different colors at different buckets and eventually you get it. And so having seen a color match, people are primed for another color match and similarly for the other categories. We did this with two different groups of rules, just as a replication that it was nothing specific about the specific rule. And you can see that there was an even larger same rule benefit with the second experiment. Okay, so basically humans have strong transfer effects. Here, just as an example, because I'm not always going to do this, but just to illustrate, here's the same data but restricted to subjects that actually solved the first rule, which is usually about half the subjects, depending on the rule. And you can see the same type of effect. It's not really a very different conclusion. That's with experiment 2. So what all that suggests is that humans have a sort of semantic space of rules, and rules have a kind of proximity structure in that space, meaning some rules are similar to other rules conceptually to humans. And that may sound obvious, but the question is whether that's true for AI, and we'll get to that in a minute. So as a way of actually visualizing the semantic space, here's an MDS multidimensional scaling solution for I'll show you both experiments. Where we basically are looking at the magnitude of transfer benefit between every pair of rules and then use that magnitude as a measure of similarity. And this is similar to a typical psych experiment where you gather similarity ratings from subjects and then see which of the objects are close to each other in the resulting MDS space. If you're familiar with this, here's what it looks like for experiment 1 and here for experiment 2. In experiment 2, it came out a little clearer. So let me show you a little bit of what the result looks like. So you can see down at the bottom, there's a cluster, and at the top, there's another cluster, and third cluster. So, oops, sorry, I thought they were sort of labeled. So the one at the bottom left, those are color matches. Those are the one on the top. Those are orders, and those are sort of reading orders, and the ones at the right, those are bucket orders. So meaning which order the bucket, the top one is which order you have to take the pieces off. The one on the right is which order of buckets you have to use. So that's an actual illustration of the semantic space that human subjects have in their heads for at least these types of rules. So all that leads to a kind of punchline question, which is there a correlation between human transfer and AI transfer? So I don't have any details on the slide about this, but we basically ran all these rules in the AI, as I said before, with various runs with different random parameters, but always the same basic model. And we're that way able, and we did them in the same sequences that the human subjects got them. And so we can evaluate transfer for the AI analogously to how we measure transfer for the humans. And here's a plot for experiment 1 and a plot for experiment 2. So again, you can see some trend in the direction of correlation, which was sort of encouraging for the AI, but it's statistically meaningless or close to meaningless, meaning the base factor is close to 1. And you can see in experiment 2, it was actually completely uncorrelated. So the punchline here is that AI can solve the rules. And I'm not saying that it doesn't learn something from having solved a rule to subsequent rules, but whatever it's learning is not correlated with what humans learn from solving a rule. So transfer in humans and AI, at least this type of AI, is basically uncorrelated. So retitling the slide, lack of correlation between human and AI transfer. So I'll just pause for a second and that's a pretty discouraging result for AI, meaning that although it can solve the rules essentially by marching through this error space, what it's doing or what it's taking away from one rule is not correlated with what humans would take away from the same rule.
This
Yeah.
is a good point for letting people ask questions if they have any, and I have one.
Yeah, go ahead.
You keep saying solving a rule. I mean, what do you mean by that? You mean discovering, you're looking for a rule for something and discovering what the rule is?
Well, for the AI, it means reaching the error criterion, um, which, you get different numbers if you use different criteria, but it just means the errors have been reduced sufficiently so that so that we count it as being solved. Of course, the errors never go down to zero. For the
There's a
humans, yeah, go ahead.
But with that criterion, there's a difference. And that's kind of a behaviorist criterion. What I mean by solving, oddly, a rule is, do you end up getting error-free performance or better performance with the task?
Well,
I'm interested whether you're really thinking of them as looking for a rule. I know what's meant by looking for a rule.
so Stephen, that's the point in a way. So what the AI is, so if I can sort of speculate past the actual results, the intuitive conclusion here is that the AI is reducing its errors, but it's not really solving the rule. It's just adopting a policy that is more likely and eventually likely enough to get to get a correct answer. But at
Okay,
that point,
in
it's simply a
that
point in a high dimensional parameter space. It doesn't have a quote unquote solution.
in that case, if they're doing that rather than solving the rule, tell me what you mean by solving the rule.
Well, again, for the AI, arguably, it's not really solving the rule. It's simply achieving low errors. Let me say, for the people, then you can ask them what the rule is. And we do ask them what the rule is, although that's not the data I'm presenting. And in their case, once they've quote unquote solved the rule, they can usually articulate the rule, although not always. But that's not the primary data. I mean, people do not always perfectly understand what rule they're even using. But the whole point is that those are quite different. So what humans are doing is qualitatively trying different rules. Again, I'm going way beyond what the data actually says, but intuitively, people are trying different qualitative rules and eventually finding one that works. The AI is essentially not. It's simply moving through this high parameter space to adjacent policies that eventually reach low errors.
Gary,
Can I jump in for a second?
Yeah, go ahead, Paul.
To say that what these AIs don't seem to be noticing is that it's a kind of rule that, for example, matches colors to buckets. So the experiment is designed with the assumption that there is a relation, that these rules are in families, and we're not seeing evidence that that is the way these AIs are solving them. I don't know if
At least not the same types of families that humans feel. There are relationships between what one rule and another rule are solvable for the AI, but I mean this is not on the slides. But for example, if you give a very similar rule but scramble it, then to people it might be very similar, and to the AI, because each of the buckets is different from where the analogous objects would have gone before, it could be a very different rule. So that's sort of the point here, is that the rules don't have the same semantic similarity to the AI that they do to humans. So
Gary,
to answer your question, what solving means for the AI and for the humans is evidently quite different.
go ahead, Gary.
Jacob, can you say more about the models here and what their prior training was, and also how are the stimuli represented to the models? So obviously shape, color, in this case, are
Right. Yeah, no,
obvious to
sorry, I should
people
have.
because, yeah.
Right. I should have said that. So, I mean, the prior training, out of the box is, as I said, it's a blank slate. But then in this experiment on rule 2, their prior training was just rule 1. So in other words, whatever parameter state they're in at the end of having achieved criterion on rule 1, that's the starting point for rule 2. So, but your other question is very fundamental. What do they actually know about the objects? So, I mean, that's a very difficult point. Meaning, what is the right way to represent this? You could, for example, attach a vision model and have it try to figure out what what features count and what. But we haven't done that. One could do that, but for the purpose of these experiments, the shape is just a feature with 4 levels, and color is just a feature with 4 levels. They don't know what shape is. They don't know what color is. And the position is a feature with essentially 36 values because there's a 6x6 grid that the shapes can appear on. It knows things like which quadrant is closer, but it doesn't have the same spatial map that a human would have visually.
So there's nothing in the input representation that makes the difference between red and green less than between red and square, right? So sort of
Correct.
within
Well,
dimension, yeah.
Well, between red and square, those differ along 2 dimensions. I mean,
Two dimension,
it does know they're different dimensions.
Yeah.
It's a little tricky. The data structure is a JSON structure which labels them, but many of the AI models are what are called one-hot models, where it's not really grouped. We're not sure that
Right, that's
it
right. The
knows
one hot
that.
means that being red and being square are both represented as sort of predicates. So
Yeah.
they're not
Yeah.
really in different spaces. That's a fair point.
Okay, we have a question from the Jean-Remy. Go ahead.
Hi, I'm not sure if you can hear me from.
I can hear a little bit.
Okay, mine's more so just a clarification question. So you said that the models were not trained on human data. Is that correct?
Correct. Not at all.
And then I guess I just wanted an explanation as to the reason as to why you decided to pick those as a form of for those models, because one could like argue that humans are trained on human data. You know, when I'm growing up as a kid, they're exposed to like other humans and they are imitating them. So I'm not sure the reasoning behind picking.
Well, that's a big question. I mean, that's what I was trying to explain before. So of course humans have a lot of training prior. That's why these transfer experiments are just about sort of if you nudge the state that the human is in when they start the experiment in a direction by giving them a rule, then the question is what effect will it have on another rule. That being said, that doesn't, of course, negate their prior experience. But and so humans, of course, have a lot of experience on, if not on this game, on similar classification problems. Um, I would, I would argue against what you just said a minute ago that humans are trained on other humans' behavior. Humans are trained. This is a big question. I don't mean to be dismissive of it, but humans are primarily trained on feedback from the environment on their own behavior. Humans are not trained by observing other humans solving the same problem before they try to solve it. They try to solve it themselves, and then whatever happens, if they get the right answer or the wrong answer, then they try to figure out the rule on that basis. Um, Humans obviously are raised with other humans and have a lot of data about how other humans behave, but humans don't solve things primarily because other people solve them first. They solve them by a combination of their innate reasoning capabilities, which is sort of what we're studying, with their direct experience with the problem itself and the feedback that they get from the environment, the world, or in this case, the game. So, I mean, that is the point that you raised, that humans are very heavily trained. Here we're trying to see whether AI in a blank slate learns, not works out of the box, but learns in the same way that humans learn, meaning when they get one particular experience how does it affect the next time they have to solve an analogous rule?
Okay, let me invoke closure now and let you go on.
Okay, thanks. Okay, so that's that summarizing so far, that's a kind of pessimistic result about AI for transfer among rules. But there's a kind of more fundamental way, I think, to look at relations among rules, which is to look at composite rules that are constructed of other rules and see what the effect is of learning a rule on a later rule that might be built from that rule. So remember, rules in the game rules can be composed, that is combined. For example, you can have like a color match plus a clockwise rule. And so I'll use the notation plus to mean that it's a combined rule that involves both concepts. You sort by color, but only in clockwise order. To just summarize a huge debate in a couple of bullet points, compositionality plays a central role in the history of cognitive science. I mean, the fact that people can build things out of parts, set of conceptual parts. It's a huge part of the debate about how human concepts work, whether or not and in what way people build concepts out of other concepts. But it's also a central issue in comparisons of human and AI performance because, because current models, no matter how good they are, there's always a question, which has many, many answers depending on who you talk to, about whether AI can combine things in the same fluid and kind of infinitely productive way that humans can, or conversely, whether it's only able to do things that it was closely trained on. So like this mirrors a famous debate in the history of cognitive science where, if you're familiar with the debate between Chomsky and Skinner, the basic argument is whether on the one hand, behaviorist models, essentially you reinforce particular behaviors, and Chomsky came along and said basically that's not enough to explain human behavior because people are able to take individual little bits of syntax or rules or meanings or works differently in different domains and combine them to form kind of an infinite range of possible combinations. And behaviorist models historically couldn't do that. And so the argument about AI is sort of whether AI is also guilty of that lack of compositionality. So with that kind of background, we want to look at transfer in a similar way to how I was saying before, but from simple rules to composite rules that are built from those simple rules. So imagine you encounter or potentially solve two rules, A and B, and then subsequently encounter a composite rule of the form A plus B. So an example, is like could be color match and B could be clockwise order, and then A plus B is color match in clockwise order. The question is your performance on the combined rule, the composite rule, affected by the prior training? So what we're going to do is compare A plus B preceded by A and B to A plus B preceded by two irrelevant rules. Equal amount of training, but on irrelevant rules, let's say C and D. So with that in mind, the first simple to composite experiment I'm going to tell you about, we had rules like this. You don't necessarily have to follow all the details of the experimental design, but we have these four rules, A, B, C, and D, and on block 3, we want to give the combined rule A plus B preceded by A and B, or potentially preceded by C and D, which are irrelevant. And similarly, we also have combined rule C plus D preceded by related simple rules C and D, or preceded by irrelevant rules A and B. So it's symmetric over AB versus CD. There's also, as usual, a fourth block, which I'm not really going to tell you about. We're mainly interested in the third block as a function of the first two. And the main dependent measure is the transfer benefit from those individual simple rules to the composite rule. So that's the key block. So there's a few details you probably don't care about that much, but like in the first experiment, A was nearest quadrant and B was reading order, C was color match and D was clockwise, etc. A plus B and then C plus D. In experiment 1B, we had, I'm just numbering these experiments to help you keep track of them, but it was a different set of rules, but the same basic structure. Okay, and so here are the results. So here you can see on the left you have the A plus B rule, this is in the third block, and on the right, the C plus D rule. And as a function of the color coding, which is what the predecessors were, A, B, or CD. So you can see, for example, in the group of bars on the left, there was a benefit for the A plus B rule of having been preceded by A and B. So that's a transfer benefit. The right bars actually don't show a transfer benefit. It's data. Humans don't always work that way. This is part of what I was saying at the beginning about not assuming behavior of humans, but actually measuring it. So the answer is there's a transfer benefit from the simple to composite rules sometimes and not other times. The other experiment with the different rules and otherwise the same experiment came out actually pretty similarly. There you can see a transfer benefit in the A plus B rule and a small, actually non-significant transfer benefit in the C plus D rule. So I'm sorry. Oh yeah, I'm sorry. That was I said that wrong. The ones on the left are the two experiments. The ones on the right are just somewhat cleaned up by only including the first block, where only including cases where they solved both of the two initial simple rules. We also looked at data where they solved one but not the other. But just to keep it simple, the issue, the restriction on the right column here is whether they solved both of the initial rules. So you can see sometimes a very sizable transfer benefit and sometimes not. So the summary is that human subjects sometimes transfer learning from rules to other rules built from them. I mean, in a sense, that's a slightly disappointing result for humans. It just shows that humans are not perfect. And some of these rules are difficult, and even with prior training on component rules, they don't necessarily it doesn't necessarily benefit them. So now I'm going to give you a slight twist on that experiment, again, still with humans. So in the ones I've just been showing you, when we had two simple rules, we combined them to form a composite rule using identical versions of the two simple rules. So that's what I would call the token. I call the token version because it's the same token individual rule. So for example, if it was a color match with a particular mapping of colors, then in the composite rule, it would be that same mapping of colors. But then we also did it with a typed version where you can see on the right the illustration here, where, for example, if it was a color match in rule A, then when it comes back as A plus B, it's not the same A, but it's A prime, which is in this case another color match, a different color match. So there the question is whether people benefit from the kind of type of rule that it is, or whether they only benefit when it's the specific rule that it was. So I hope people see how those experiments are different. They're both about transfer from simple to composite rules. But the question is, does it matter whether you saw a specific instance of a rule or just something like it? So I call that the type version. So here's a schematic of the experiment, and you can see it's the same as before, except these primes indicate that the second time a rule appears, it's not quite the same version. But the main dependent measure is, again, performance in block 3 as a function of the preceding blocks. So here are some details of what the rules were. Again, I don't think people necessarily care about the details here. Let me skip straight to the results. And you can see kind of similar results to before. Again, the transfer benefit is when, for the rule, that's the group of bars, is better when the predecessor was the same rules, like A and B, when the composite rule was A plus B, or not. And the answer is, in some cases there is transfer, in some cases there isn't transfer. It's actually broadly similar to the results with the token version. In other words, in very broad terms, to humans, when they later subsequently encounter a rule of the same type, it's kind of the same as if they encounter a rule that's exactly the same one. They don't necessarily even notice. I would say intuitively as a subject, you don't necessarily notice if the mapping from colors or shapes or whatever is precisely the same, because that's not conceptually how you represent the rule. You represent it as a kind of color match or a shape match, and if you see another color match or shape match, you're primed. So the results are very broadly similar to the token version. People sometimes, although not always, can transfer from one rule to another related composite rule. So but now the punchline that you might be waiting for is what about the correlation between human transfer of this type and AI transfer of this type? And here there aren't very many points, because we really just have one transfer benefit for each rule pair. So it's a total of 6 across the experiments. It's a total of 6 points. And here you can see again on the x-axis the human transfer benefit from simple rules to composite rules, and on the y-axis the AI, which is exactly the same. I didn't say this, but we ran the AI on the same sequences of rules, precisely the same sequences of rules. That's the whole point. Here you can see the actual numbers, by the way, on the x-axis, how these numbers are kind of small, 20, 40, 60. And on the y-axis, they're up into the thousands. But the punchline is that you can see that this scatter plot is pretty much random, meaning that there is basically no correlation between the AI transfer and the human transfer. Again, a kind of disappointing result as far as the effect, as I was saying before, the effect that one rule has on a subsequent related rule. So the summary is that AI, although it learns from individual rules, it doesn't do so in the way that is really correlated in any meaningful way with the way humans do. Okay. So that's the main empirical result. And let me just move on to sort of some questions one might have. So first of all, what about LLMs? I mean, I think a very natural question here is what if you had a model that was trained on human behavior? And that's maybe implicit in the question somebody asked before. Um, so, uh, you know, everybody knows, I think, what LLMs are. And you might ask, can they solve GOHR problems? So I'm going to be very brief about this because it's not the main result here. But to test these models, we tried. This is Vladimir Menkov, a collaborator on the project. Basically did this in a number of ways. For example, giving the LLMs random moves or giving them only positive examples, only moves that worked, or only negative examples, only moves that didn't work, or in some cases also giving them just human-generated moves, meaning giving them moves from a transcript from one of the experiments, and then ask the model, the LLM, to either choose the next move like a human would be asked to do, or to describe the rule verbally. And so that's kind of analogous to what a human would be asked to do. So before I give you any kind of results or details, let me say that the training data, of course, included. This is text. These are text bots, chat bots. So the training data potentially includes people writing about solutions to similar problems, potentially including our actual experiments. We didn't have any way of checking whether the training database includes anybody who might have run one of the game of hidden rules experiments. Probably not very much, but certainly there are very many similar games or similar situations where people talk about classifying things. And so in a sense, the AI has been trained on something that is related. So I don't know if that's a caveat or it's kind of a feature, but that's partly how these models work. So a couple of details. So first of all, we used Gemini, which is Google's AI. And I want to say there was a marked improvement from early versions that we tried a year or two ago to current versions. So if you know the Gemini versions, from version 2.0 to the current version 3.0, there was a substantial improvement. Just to give you a sense, earlier versions did not seem to even understand the game. For example, they would propose moving objects that weren't actually on the board, or they would sometimes repeat a move that had already been tried and hadn't worked. In other words, they didn't quite get the spirit of the game, but the current versions do. So that's a pretty impressive improvement, and they can kind of play this game. I mean, as I said at the beginning, this is not the main focus because I'm not interested in personally in whether these models can mimic people, which is essentially what they're doing here, but rather whether they do it out of the box. But they in a very broad sense perform about at the level of people. They asymptote after at some level somewhere between 60 and 100% after about 2 or 3 boards, which is about how many boards that people take. Each board has typically like 20 pieces on it. So it's sort of very broadly comparable to humans. But I will say the bot's behavior was inconsistent. So this will sound familiar to anybody who's studied modern LLMs, but they would, for example, sometimes propose moves that contradict the stated rule. So, for example, it's like saying, I think it's a color match where red goes to bucket 0, but then suggesting a move where a black shape goes to bucket 0. So there's a cliche about these things that LLMs are trained to chat, not to reason. Um, they're inherently trained on text material, no matter what the bias is within the model. And you can see that in the results somewhat. We did do some very microscopic amount of training on completely novel problems that weren't included in any published version of the Game of Hidden Rules. And they didn't do very well, but I don't really think it's fair to hold that against them because we don't know how people would have done on those rules because we never ran them. So by definition. So let me just say these LLMs can kind of do this, but they don't do it. But they do it based on training on similar problems from humans, which of course as I was saying before, I don't think humans have detailed data about how other people solve the similar rules. They only have data about how they have solved previous rules. So the transfer results were pretty disappointing. AI does not transfer the way humans do. So I want to just stop for a second and say, wait a second, but the AI can learn, right? And let me just emphasize, the AI models show plenty of signs of learning. They do learn how to solve these rules. When trained on a rule, they become proficient at that rule. That's essentially definitional to how we set the criterion. But I just say this to make sure we keep in mind that they do learn individual rules, and further, and this goes beyond anything I said, they also can learn sets of rules. So if you train them on a set of rules like A, B, C, then they learn rules A, B, and C. Um, in part, they do that by classifying which inputs correspond to which rule, which is itself not an easy problem. So in other words, if you're an AI that has already learned to solve rules A, B, and C, and then you encounter another problem, one thing you might ask is, does this problem fit into one of my three previously known rules? And the answer is it can solve that problem, but that itself is a difficult classification problem, and they can do it, somewhat noisily. And we've done that, but so it can be done, but even that is kind of difficult. So this again should remind you of kind of classic behaviorism, where the debate was, does the rat only learn the specific things that we trained it to do, or does it learn some kind of generalization that it can apply productively to future problems? And the answer in behaviorism seemed to be that it can only learn specific behaviors, which is partly why behaviorism went out of fashion.
I have a question
Yeah, go ahead.
about what you just said before. Unless I misunderstood it, you said that there are also cases where the model learns the right rule and violates it.
That's the LLMs. So I'm sorry, now I'm talking about the regular reinforcement model. The LLMs will say things and do things that are inconsistent with each other. These are only the A2C model is only proposing rules. It doesn't have a verbal description, so there's no inconsistency. The question is whether it can whether it can learn productively from individual rules, and the answer is it can learn a finite set of rules, but it can't generalize from those rules in a way that resembles the way people do.
Okay, thanks.
So to understand the differences here, let me just kind of talk about degrees of generalization. I mean, contemporary AI can generalize beyond its training data. That's well known. The question is essentially by how much. So let me make some distinctions and some terminology. So for people who are knowledgeable about AI, this is just kind of standard definitions. There's what's called out of sample generalization, which means typically like you hold some fraction of the training set out of the training and then use it for evaluation. That's routine in current machine learning, and machine learning wouldn't work if people didn't do that, and nobody would care if it worked if it couldn't do that somewhat. So this is like cross validation. So AI can generalize to data that it hasn't actually been trained on. But that's not really the hard question. The question is whether it can generalize to data that's drawn from a different distribution from the data that it was trained on. Now, I think, pausing for a second, I think to AI people, that would seem like an unfair question, because why would you want it to learn from one distribution to apply to a different distribution? But nevertheless, that's really the question, or it's at least a step towards the question, because that's what people are good at. People are good at learning from one situation and applying it to a situation that may have somewhat different rules or different processes or different details, but nevertheless is in some sense analogous enough that people can learn. That's out of distribution generalization. But let me distinguish that from sort of far out of distribution generalization. And I mean, by that, I mean things where there's an analogy from what you've learned to what you're subsequently encountering, but it's such an abstract analogy that it's not just a slightly different, but like parametric version of the distribution, but something grossly different. And I mean, to me, the quintessential example of that is what people originally were good at in our evolution, which is that we were able to, we evolved on the savannah and were able to figure out how to make a living and find food and survive in the savannah. But then whatever changed in people's brains around the time that we separated from other primates, we became able to solve problems with such a degree of abstraction that people were able to migrate out of Africa and live in extremely different environments. So living in the snow, like in Northern Europe and in the ice ages, or living on the ocean as people migrated along the Asian coast, eventually making it to North America many millions of years later. The way that you survive living, off of shellfish, and the way that you survive living in the savannah are not just a little different, but completely grossly different. And people were able to cognitively make those generalizations, whereas other species generally can't. So that's I mean, that's an extreme example, but that's the type of far out distribution generalization that people can do. Um, so that's what makes people intelligent. So let me summarize by saying, well, we test. I mean, so this is just a nominal summary, so make sure everybody followed it. We tested AI and HI on simple rule discovery paradigm, and people can solve this, AI can solve it, but AI does it much more slowly. It does share certain gross characteristics with human learning. There are complexity effects I didn't actually talk about. People find more complex rules more difficult, and AI also does. So it's not like completely different from human performance. But the punchline is that AI generalization from one rule to another is mostly uncorrelated with human data. And my summary of that is that there is something deeply wrong with contemporary AI, meaning obviously it can perform very well, and you know, I'm very impressed with modern AI as everybody else is, and it represents a degree of performance that I personally would have found absolutely impossible to believe, you know, 20 years ago or 30 years ago. But nevertheless, it's doing something that is qualitatively different from what people are doing. The reason why it works is because it is trained on human performance. And if you take away, I mean, that again, that might sound silly to a contemporary AI person to say that you take away the training on human data. That's the whole point. But that's not how people are trained. People are trained on feedback from the environment. That's so-called reinforcement. And in that sense, reinforcement models are maybe a better analogy to what, you know, to how humans actually reason. But there's other problems with reinforcement models. But in any case, conventional AI that's based primarily on a huge training set is deriving its qualitatively good behavior on the huge training set. So, and that is humans, you know, having done it before. So I kind of final remarks. I personally don't like these kind of hand wavy generalizations like AI just imitates and people comprehend. That begs the question of what comprehend actually means. And as I said at the beginning, comprehension is something we are trying to understand in humans, and it is some sort of computational model. People are doing something, and I don't personally think that that's not computational. I think it is computational. The question is not whether computational models can do what people do. The question is whether current models, the way that work that work the way current models do, are doing it. So that being said, there are large qualitative differences between AI and human generalization from problem to problem. And that's what I was showing you, this kind of lack of correlation. So just to kind of give you a sense of how I think about this, there's this cliche that Paul Cantor, who's on the call, shared with me years ago that mathematical intuition means you've seen the problem before. This is just referring to people. When somebody seems to like get it quickly, often it means they've seen it before. And you know, people can learn from one example to a very similar example. People are very good at that. So in the same spirit, what currently passes for artificial intelligence kind of means the bot has seen the problem before, not precisely because it does generalize somewhat, but it's something very much like it, meaning it has seen a person um, solve the problem or some problem very similar to it previously before. So the AI is in that sense fundamentally imitative, whereas it's not actually, so to speak, thinking. It's simply statistically imitating how people think. So as a kind of final comment about the Turing test, I mean, for an AI to really count as passing the Turing test, it has to be able to do it without first being trained on how people would have solved the problem. So the kind of my cliche that I like about this is anyone can sound like Frank Sinatra in the shower. I don't know if current generation is familiar with Frank Sinatra, but the point is when you sing in the shower and just listen to yourself, you can sound great. Um, and in a sense, you sound great because you're trying to do it the way Frank Sinatra, a great singer, would have sounded. The problem is that Frank Sinatra had to do that without having previously heard Frank Sinatra. So I'm not sure if people buy the metaphor, but modern AI is like singing in the shower. It's imitating what people did first, and it's not clear to to just say it gently. It's not clear whether AI can reason out of the box without first being told first being guided with how to solve it by previous human performance. Now, final point for AI researchers, I don't think they mind that it's being trained on humans. That's the trick that has made it all work. And it does work. And from a technological point of view, that's very impressive. But in terms of understanding human intelligence, they're approaching the problem in a way that's quite different from the way the brain approaches it. And I think you can see that in some of the forward transfer data that I showed you today. I believe that is it.
Okay, we'll applaud, but that doesn't mean there won't be questions coming.
Yes, I know.
Okay.
Thank you.
If the floor is open, you have less than a quarter. You have about 12 minutes to avail yourself of that.
Okay.
Gary first, and then
Yeah, go ahead. Gary, go ahead.
Oh, I want to push a bit on this issue about, Frank Sinatra had to do it without imitating Frank Sinatra. It's true, but Frank Sinatra did not invent singing. And Frank Sinatra had plenty of other models. And it's not clear to me that people can reason on your definition of out of the box, right? So the participants you're testing, of course, are adults. And even if they have never done this game before, they speak a language which categorizes things by shapes, by colors. They have played games. They know what a goal is. They know, right? So they're coming in with tons and tons of knowledge. And so, is it really fair? Like, what is an out-of-the-box model analogy, right?
So Gary, so I agree with that. I mean, I want to explain.
Yeah.
So first of all, you're absolutely right that humans come with it in a lifetime's worth of experience. So I'll get back to the Frank Sinatra point in a second, but and that's why I think a comparison of AI and human performance out of the box is not really fair. So that is the first thing I showed you, that that there's very little correlation between how humans and AI solve these problems initially. That's why that result by itself is not very impressive, because of course they have very different training. That's why we did all the transfer experiments. With the transfer experiments, the issue, of course they do still have different background training, but there the question is, what is the effect of a new rule, specifically in this context, with the rules of this game, on a subsequent rule? And there you're taking the human in its state and sort of taking whatever point it's in and perturbing it to see what direction it moves when you hit it with a rule, and then taking the AI in its state and training it on one rule, and then perturbing that to see what direction it goes. And the answer is the directions that they go are uncorrelated. So that is a more fundamental test of whether the learning is similar, putting aside the background. Of course, there's no way to test humans out of the box. I mean, I'm sorry, in a sense, that's what developmental psychology is about. And there, the general finding is that people, are not blank slates when they're born. But that's not what we're doing. What we're doing is looking at a fully trained human, and we can't have a fully trained AI in exactly the analogous sense. But what we can do is look at this, what I'm describing as perturbation, and there, the directions that they are pushed in by a particular rule are uncorrelated.
I would add that we haven't yet done the transfer experiments with the strongest contemporary LLMs. These data were for laboratory learning algorithms.
Right, but we haven't done transfer experiments with the LLMs. We've only done initial performance evaluations. So I think that's next.
Okay, Christian, go ahead.
Thank you. So how does the game of hidden rules and the result compare to similar challenges like François Chollet's ARC challenge, and even some popular ones, like, for example, people who play the New York Times Connections puzzle, which is about similar sort of grouping of categories that are partly semantic, partly linguistic?
Well, let me first say I'm not an expert in all of those, and I can't really comment. But again, that was the logic of the transfer experiments, is that it's not important, or it's not quite on point, to ask whether the AI can do what people can do out of the box. And the question is how is it affected by experience? And meaning that's the question as I'm framing it. And so I don't know if those experiments involve those as well. If they do, then I would suppose they're analogous. But I think they generally don't. It's about whether mostly that sort of contemporary experiment is about whether LLMs usually can can perform the way people perform, which is a way of asking whether their generalization from prior human behavior is sufficiently rich to capture other human behavior, which is a good question, but it's not the question we're asking.
I guess the direction I was going to is that to some extent the devil's in the detail, as the comment about the difference between the one-hot encoding and the JSON representation was. So for example, the ARC challenge pushes pretty solely in the visual directions, right? Whereas the New York Times connection is more like a mix of linguistic and semantic. And it would be interesting if in different domains we'd get different results because the representation is different.
Yeah, so I mean that's something that I think about a lot. We don't have a great answer for it, but just as an illustration of what you're saying, you know, an obvious initial experiment to do with humans, which we did at one point, is, for example, whether shape matches are easier or harder than color matches. But that's not really a meaningful question for the AI because they don't know its shape or color. They just know the one-hot representation, and so those are effectively the same. At least the way we're representing it. It doesn't have to be. You know, you could, as I said before, you could give visual input, but the way we're representing it in the experiments I told you about, there's essentially just, you know, abstract features. And so obviously to people, they're not abstract features, and there's a color space and there's a semantic space among rules, and the AI doesn't really have access to that.
Thank you.
Jean-Louis.
Hello, thank you for the nice talk. Gives much to think about. I have a question about ask you for your thoughts about the fact that the game is about compressing, in the sense of a Kolmogorov complexity, that you have to compress, find the simplest possible rule that says to you what to do next, and so it's a compression task. And it seems to me that your claim is that the way human beings compress information in this kind of task is different from the way machines do. So I know you are aware of the role of Kolmogorov complexity in cognition. So what do you think? In the light of complexity, that we do not compress the same way as machine, who are more efficient.
That's a very rich question. That's a little hard to answer, but exactly what people are doing when they solve these rules is, I mean, we don't really know. But my intuition about it, and we have kind of models that we haven't really fully tested yet, is that people represent the rules in a kind of combinatoric space, meaning that you have some sort of notion of color matches, for example, or space or order. And you can try rules essentially in complexity order. I mean, I'm not saying that people strictly do this, but one would typically try simpler rules which have higher priors, if you think of it as a Bayesian, in a Bayesian framework, and try more complex combinations later on. And you know, in that sense, you're going to stop with the first rule that you hit that works, which means if you do them in complexity order, it's going to be roughly the simplest rule that explains the data. The kind of the argument about transfer in AI is that it's not doing anything that could really be analogized to that. It's moving in a gradient descent through this very high dimensional space, and when it hits a policy that has sufficiently low errors, it stops, or we stop it. And there's no analogous way of expressing it in terms of a reduction in complexity. So what I just said really goes beyond what we really know about how the AI works, because it's a little bit of a mystery what happens inside the parameter space. That's something that Hao Wang is working on, trying to develop a more interpretable expression for what the machine is doing at any given point in its learning. But I think the results of the transfer experiment suggest that it doesn't have any kind of compressive interpretation the way that humans do, at least not in the same space.
Okay. Ken Wolfenden seems to have left. He had a question as well, and we only have 3 minutes left anyway. So does anyone have any way to use the 3 minutes, or shall I just thank Jacob for giving us a very stimulating and thought-provoking and informative talk? Thank you.
Thank you, Stephen.
Thank you.
Everyone for listening.